Hi again. So in this video, we're going to check the conditions to perform inference for the Elmhurst problem with the slope. And then we're going to go ahead and do the hypothesis test and confidence interval. So I'm going to follow the steps just along with this box on the last page. Okay, so I'm going to start with the conditions, then do all this. Okay, so let's go for it. Okay, so have that page handy. So the first condition is linearity. Check the scatter plot for a linear pattern. Okay, so you remember in a previous video, we did look at the scatter plot and it did look really linear. So I'm going to write the scatter plot. Has a linear pattern. In other words, it doesn't look curved. Okay, so that one is good. Next is independence. Okay, so the students selected, so the subjects selected, and they're randomly selected, must be independent in terms of both variables. In terms of family income is the X variable, and award or aid amount. Okay, so what are some things we should consider here to make sure we have a good random sample? Unbiased. Well, we wouldn't want any siblings, right? Because they would not be independent. They'd have the same family income. So I'm going to say no siblings. We want to think about both of these things, like what are some things that would make students independent in family income? We might think of like geographic area, urban versus rural. Even different states might just have higher cost of living than others. So I'm going to write location. We always want to look at gender, race and ethnicity. And then also thinking about award amount. Maybe all the students randomly selected had higher GPAs or lower GPAs. So we would want to make sure that we were looking at that as well. So different GPAs and those other factors that we thought might contribute, all those other factors. Other award factors. Okay, so we want to make sure that our random sample is unbiased. Then the next one, randomization. We do have a random sample. We have, or I could say we need, but in this case we know we have a random sample. I'll just put of 50 students because I know that. That's going to come up more in the sample size though in just a second. Sample size. Okay, our n is greater than or equal to 30, so we don't need to check the nearly normal of the residuals, although they did look roughly nearly normal. We could graph the residuals on a little better graph to see that better, but they looked fine to me. And then the last one, this newer one, constant variability. Of the residuals. Okay, so this is when we look at the residual plot. I'll just remind you of that. So we have our residual plot right here. It looks fairly evenly scattered. I do notice there's more down here, more students down here than up here, but there's no really difference in the variation up and down between those. So I'm not too worried about that. So I would say that scatter plot looks evenly fairly evenly scattered. Oops, just trying to get rid of that thing on there. Okay. The residual plot. Looks evenly scattered with no patterns. Okay, great. So those are our conditions. So I'd say we are safe to continue. So it says to test whether the slope is negative with a significance level of 0.05. Form the corresponding confidence interval for the slope and give the interpretation. Okay, great. So we want to test whether the slope is negative, and just like we're used to doing, forming the corresponding confidence interval. Okay, and then we'll do our conclusions. Okay, so let's start. So now I'm going to go to our hypotheses here. Our null is going to be that there is no trend, so its beta is 0. And beta is like a bee with a tail on it, so I start down low. The null is that beta is 0, and we're testing whether it's negative, so our claim will be that beta is less than 0, okay? And I'm just going to write down our degrees of freedom is n minus 2. So that's going to be 50 minus 2 is 48. We will need that. And just for kicks, I'll write down our alpha to 0.05. So I've got everything right there. Significance level of 0.05. Okay. So now in our test, we need to look at our t statistic. So we need to find our observed statistic minus the null over the standard error. So I'm going to write down this formula right here. So I'm going to write down t equals b minus 0 over the standard error. Now we haven't talked a lot about the standard error yet, so I'm going to show you how we're going to find that. We're going to use Staplet. So there's a formula for that, but we're not going super in depth in this topic. It just kind of goes beyond the scope of our class. So this is where we're going to use the advanced, or I forget what it's called. Let me go back to Staplet here. The more detailed regression output, that's what it's called. So we're going to use that. And look what this shows us. So we have two rows, one for the constant. So constant is the y-intercept. Think constant does not have the x by it, doesn't have a variable, so it's constant. Family income, this is our y variable. Family income, sorry, that's our x variable. This is we have our coefficient, we have our standard error, we have our slope. Yeah, it's interesting that it's the slope, but they're giving the x. I guess they do this for each variable, each explanatory variable, even though we're actually studying the y, right? And the slope is a combination of x and y. But the one that has the variable name, that's going to be related to the slope, okay? And you can see a t statistic right here and a p-value. So we're going to check and see if we get the same thing, okay? You can also test the y-intercept. I just don't really have a desire to do that right now, but in a different circumstance, that might be useful. So this is our b, the coefficient, and you'll notice it's the same as our slope right here. It is rounded slightly differently. It's only rounded to 4 digits here, and it's 5 up here, so either way is fine. So that's our b, and here's our standard error, 0.0108, okay? So remember, this is sample to sample. So if we had this one sample of 50 students, right? What if we took a different random sample of 50 students and a different random sample of 50 students? This is the sample to sample variation between them, okay? So it's calculated using a formula, and we could do simulations as well, but we're just not gonna go that in depth right now. So I'm gonna go ahead and write the b, and then I'll go back to the notes. So negative 0.0431, I'll just stick with the rounded one, minus 0 over 0.0108. Okay. Go back to the notes here. Okay, so that's the b. You don't have to write the minus 0. I'm just writing it to show you this time. And then if we divide that, we get our test statistic. So I'm going to put negative 0.0431 divided by 0.0108. Notice it's going to come out negative. Negative 3.9907. Okay, let's compare to what it said the test statistic is. Okay, very close. So I wonder if they're actually using more digits here in the calculation, but it's very close. And then now we need to find our p-value, right? They don't give us a very accurate p-value here. So for the standard error, let me make a note here. For the standard error, we're going to use a Staplet. For the slope as well. But we're not calculating the standard error ourselves. Now to find the p-value, we need to go to use the t-distribution. So the p-value, let me switch colors here. The p-value is the probability that the test statistic is less than negative 3.9907. I'll do approximately equal, and so we're using Staplet t-distribution for this. Okay, now this is almost 4, so I bet you know this is going to be very small. Let's check it out. Okay, so Staplet t, or you can go right there. P-value is an area. Degrees of freedom, we already calculated that, is 48. And then we have a left tail test here, negative 3.9907. Show labels on plot. Okay, so here I'm getting 0001. Okay. Great. Okay, so 0001 is a little more accurate than going back to this one on regression, less than 0.001. So you've probably figured out that this might not be accurate enough for my open math, so be sure to find it on the t-distribution, okay? Okay, great. So let's go back to the notes. Okay, so we have a very small p-value, so that is significant. Let me just write that is less than 0.05. So we have strong evidence that we do have a negative slope, right? Okay, now I could wait and combine all my conclusions at once. I'm just going to do them separately here. With a p-value of 0.0001, and you're really good at this. At this point, we reject the null hypothesis. So you could even pause and try writing it out yourself. There is evidence, strong. There is strong evidence of a significant negative, and I'll write linear because we're only, this only works for linear right now, negative linear relationship between, notice I said relationship, between family income and award amount. And that also doesn't mean that's the only factor, right? Because we saw with the R squared was only about 25%. So there's other factors as well, but this does appear to be a factor, right? Okay, so this is really interesting because it tells us we have a significant negative slope, but it doesn't tell us how negative it is or what the slope might be, right? So it could be negative but very slightly negative, or it could be, have a really negative value. So that's where I'm sure you're you're chiming in to yourself, like that's where the confidence interval comes in, right? That's why we need the confidence interval to actually get the estimate of the effect of how negative it is, okay? So let's do our t interval. Move this up a little bit. Okay, so we'll do our t interval, and the formula for that is the slope plus or minus t star for the degrees of freedom. Oh, we need to figure out our confidence level, right? Times our standard error. So that's the same standard error that we used before. So let's figure out what our confidence level is going to be. Let me write the formula first. T interval is going to be B plus or minus T star, and I'll put 48, oops, not 44, put 48 down here, times the standard error, okay? But we know to find our T star, we need to know what confidence level that is. So I'm going to use that formula, C. This was a one-tail test, right? This is a left-tail test. So the formula is 1 minus 2 times alpha. We need 0.05 on each side. So together that's 10%, so this is going to be 0.90. And if you prefer to draw it out, that's what I usually do. 0.05, 0.05, because it's a one tail, we need to mirror that in the other tail. That leaves 90 in the middle. Okay, great. So now we can do our formula. Let's start with our slope, which is negative 0.0431 plus or minus. Okay, we need our t star, right? So let's go back to our t distribution. T distribution, and a t star is a value. Same degrees of freedom, 48, but we need to go central because a confidence interval is central and 0.90. Okay, right, so that's saying we need to go out 1.6772 standard errors, plus or minus on both sides, to capture the middle 90% of all the possible random samples, right? So let me write this down. 1.6772, and then we need to write our standard error, which again is the same one we just used, 0.0108. Okay, so that is our confidence interval, and you can use Desmos, of course. These are not too many calculations, so I'm just using my calculator. 1.6772 times 0.0108. So together that's the margin of error. So I like to do that first. And it looks similar, but a little bit different. Negative 0.0431 plus or minus 0.0181. Okay. Interesting, I got a slightly different answer when I did it before, but I think this one is correct. Just double checking. 1.6772. Make sure I don't make any mistakes. 1.6772, yep, times 0.0108. Okay, yeah, must have done something wrong last time, or maybe I got a 6 instead of a 7 there. Okay, so that's our margin of error. Now we can add and subtract, or subtract and add. Negative 0.0431 minus, remember the negative is different than the minus on this kind of calculator. The negative is down here and the minus is over here. Different than an operation. minus 0.0181. So negative 0.0612. And then the plus, negative 0.0431 plus 0.0181. Negative 0.025. Okay, now remember this was per dollar. And so I do want to do that same conversion that we did before. So let me just remind you what this slope is. This is for the slope. So this is a rate. So the units here are dollars in award per dollar in income. Literally per $1 in income, okay? So this would be from this to this, dollars in award per dollar per every increase of $1. Let me just put a 1 in there, $1 in income. So I thought it would be a little bit more meaningful to change that to per $1,000. Now you don't have to do that in every, every context is unique. So I'm going to do again times 1,000 times 1,000. Which means I'm going to multiply each of these by 1,000, okay? It should move the decimal over 3 places. So negative 0.0612 times 1,000 is 61,123, $61.2. So it's 61.20. And then do the same thing with the other one, negative 0.025 times 1,000. Yep, 123, 25 to negative 25. Okay, so now this is dollars in award per $1,000. Okay, so essentially the numerator got multiplied by 1,000 here and the denominator got multiplied by 1,000 here. Okay, so again, you could do it either way. I just finding it a little more meaningful to do it this way, and it's just a good example to show you as well. But you could also keep it per $1. Okay, so let's go ahead and interpret this. And it's negative to negative. So remember what that means? That means 0 is not in the interval. So this is significant. And remember when it's negative to negative, we flip it and use the word like decrease by, because it'd be hard. Let me go over here because I'm going to interpret this one. It wouldn't make any sense to say from this to this. So we're going to say from $25 to $61.20 decrease, right? Okay, so let's write that out. Pick a color here. So with 90% confidence, the average decrease, so there's my negative sign, in aid award is 25, get my dollar sign in there, $25 to 61.2, or I could leave that off, $61, for each $1,000 increase in family income. Okay, slope is always a rate of change. It's always has 2 units because it's the change in y over the change in x. So we always want to make sure we get that for each and then get the x in there as well. Okay, so hope that's making sense so far. Now we want to talk about whether they agree or not, and because 0 was not in the interval, and it's a left tail test, so because the whole interval is negative, that's also going in the correct direction, they do agree. So I'm going to write that we rejected the null hypothesis, and the whole interval is below 0, the null value. So the two methods agree. Okay, great. Okay, great. So we went through the whole process. Now I want to show you how to check that. I'll go to the next video. I'll show you how to check this by doing the actual inference in Staplet. Okay, great. I'll see you on the next video.